Our topic this week is inference in probabilistic graphical models. That is, we're aiming to answer the question, given a probabilistic graphical model, either a Bayesian network or a Markov random field, we want to be able to do probabilistic inference. That is, output the probability of certain events according to that model. Specifically, this week we're going to focus on exact inference. That is, giving you an answer for that question exactly. Next week we're going to focus on approximate inference. As we're going to talk about today, in general, inference in probabilistic graphical models is computationally hard. We're going to look at a couple of cases where it's tractable, but there are going to be a lot of cases where it is not. So for those, we're going to need to resort to approximate inference. But this week, we're going to talk about methods for exact inference. So this is, we're going to switch this week to kind of more of an algorithmic focus. I would say so far we've had more of a mathematical focus, that is aiming to derive expressions for various updates, and only in a couple cases, like in the case of optimization, we focused a lot on the actual algorithms. These 2 weeks are going to be very algorithmic. That is, we're going to be looking at how to do these computations computationally efficiently. Okay, let's say more specifically what we mean by probabilistic inference. That is, we have some big Bayesian network or Markov random field with some perhaps complex structure. And in general, we're going to divide our variables into 3 sets. We have our query variable. That is the variable that we want to know the distribution over. Let's say, in this case, that variable is b. We have a condition or an evidence set of variables. Let's say that's d equals 1, e equals 0, just making up values. And we have our hidden or variables we don't care about, which is everything else. In that case, that's a and c. So that is, we're trying to answer the question, what is probability of b given d equals 1, e equals 0. So notice that if I want to write down this expression of probability, I put b in front of the condition because that's our query. I'm putting d equals 1 and e equals 0 in our evidence. And then the hidden variables, the don't care variables, they don't appear anywhere in this expression. By the way, we could have said we want the probability of b equals to a particular value, let's say 1. What we're going to do in general for these algorithms is we're going to give you the whole distribution over b as output. By the way, we're going to focus here only on discrete inference. That is inference over discrete random variables. All of the algorithms we're going to talk about here extend to continuous random variables, but things get more complicated because we need to represent the distributions over those variables. We can't represent them explicitly because that would require writing down an infinite number of probability density values. So we have to represent them with some sufficient statistics, and that becomes complicated. So we're going to focus just on discrete random variables here. Also, we're going to focus on cases where we have a single query variable. We could imagine queries also of the form like B equals 1 and C equals 1, but what we might want to know the case of that event, both of them happening together. There exist methods for those, for that question, but they get a little more complicated. So here we're going to focus just on the one query variable case. So mathematically, this is easy, right? We've done this 100 times before. If we want to know this conditional probability, we just need to plug it into Bayes' rule. This equals probability of B, D, E. I'm not going to bother writing the actual values just for simplicity, divided by probability of D, E. So that's easy, right? And then notice that we're given a Bayesian network or a Markov random field. That probabilistic graphical model doesn't actually specify either of these distributions. So in order to actually plug it in to our probabilistic model, we need to marginalize over the variables that aren't present. That is, we need to expand this into the following. Our Bayesian network or Markov random field gives us this full, complete probability expression. So we have to marginalize over the hidden variables, sum over all the possible values of A and C of probability of A, B, C, D, and E. Notice that now we have values for each of them. A and C we assigned in the sum, D and E we assigned in our evidence, and B we're gonna we could imagine assigning it here as our query, what's the probability of B equals 1, or we could just go through them one by one and do this calculation. If what we want is a distribution over, let's say, the 5 values of B, we could just do this calculation 5 times for the 5 possible values of B. And then same thing goes in the bottom here, but notice that we have to sum over B as well because that's part of the query. Okay, so like I said, mathematically it's simple. Why is it difficult computationally? So for a couple of reasons. Number one is because of hidden or don't care variables. So notice here that I have to sum over all the possible values of A and C. So if there are variables in my network that I don't care about, counterintuitively, that actually makes inference much more challenging because, again, I have to sum over all the variables. And for a network that's really big, like let's say we have something like this, where here I'm using Q for a query variable, and then we have a whole bunch of variables we don't care about, and then we have some evidence over here. In order to figure out the probability of the query, in principle, we have to sum over all the possible values of all of those intermediate variables. This is also hard in Markov random fields because recall that in a Markov random field, just to calculate the value of a given joint probability, that's given by 1 over z times some product over our different potentials. And recall that to figure out what 1 over z is, or to figure out what z is, we need to do a sum over all of our variables. So in general, when someone hands you a Markov random field, you would love it if they handed you the z value, the partition function, but in general they don't because it's so computationally expensive to calculate. So for Markov random fields specifically, we're going to assume we haven't calculated that 1 over z value. Now that's not necessarily an issue. It doesn't necessarily make things any harder than they would be otherwise, because notice when we apply Bayes' rule, the 1 over z occurs both in the top and bottom of the expression. So generally, we can just ignore it in our calculations and just figure out the numerator and denominator and then divide them without having to explicitly factor in the partition function. But in order to get this denominator, we still have to do this big sum over all the variables in the network except for the ones that we've explicitly defined according to our query and our evidence. So it's kind of two sides of the same coin. In all these cases, the big issue is that in general, there are usually a bunch of variables that we don't care about, and we have to marginalize over them, which involves a big sum. By the way, in networks where you have evidence for almost all the variables, that is in general computationally easy. So the place where we need to worry about algorithmic issues for probabilistic inference are cases where we have unobserved variables. So that occurs very often in machine learning, of course, because there's generally two categories of unobserved variables. There's the labels, things we want to do inference about, and there are parameters. We're going to talk about two algorithms for exact probabilistic inference this week. The first one is going to be the belief propagation algorithm, which we're going to apply specifically to tree-structured probabilistic models. And I'll tell you what I mean by that in a little bit. The second one is called the variable elimination algorithm, which applies more generally. So the reason to focus on these two, the variable elimination algorithm is, like I said, it's general and it's quite useful. It can be less efficient than an algorithm called the junction tree algorithm, which is a general case of the belief propagation algorithm on trees. So we're not going to talk about that junction tree algorithm. It's a little bit too mathematically heavy. It would take a little bit too long, I think. It's described in the book, and I encourage you to take a look. You'll find if you read through that section that it's a relatively simple conceptually, but mathematically and sort of notationally challenging extension of the belief propagation algorithm. So that's the main reason to discuss belief propagation. I would say there's two reasons. Number one is what I said, is if you understand the belief propagation algorithm, you will be pretty close to understanding the junction tree algorithm, which I would say is the most widely used kind of heavy lifting algorithm for probabilistic inference in probabilistic graphical models. And second is that tree-structured probabilistic models, again, which I'll define coming up, do often occur in practice, and so it's often applied there. So those are those two methods we're going to talk about. Belief propagation for trees and variable elimination. Before we discuss the algorithms specifically, let's define a few things. The first is a factor. So by factor, we just mean a probability table over some set of random variables. So if I write f of a, b, and c, I could write this down as some table where we have a, b, and c. And for every possible assignment, here we're imagining A, B, and C are binary, but they don't have to be in general. There's some value of f of A, B, and C. And we're not going to require that this factor be normalized, they could be any arbitrary values. We're also, so factors are more or less the same principle as a potential that we defined in the case of a Markov random field. Recall that a potential over some subset of variables is also a probability table, or not necessarily a probability table, a value table over the possible assignments to those variables. And in fact, potential functions are an example of a factor. Another example of factor would be our standard probability function. If we wanted to write down probability A, B, and C, we would represent that as a probability table over all the possible assignments to those variables. And in that case, our values would sum to 1. Another example is if we wrote probability of A, B, given C. Note that that expression still gives you a unique value for every possible assignment to A, B, and C. But note that this won't all sum to 1. If you took all the values, if you hold C fixed and look at and all the values of A and B and sum those up, then you'll get something that sums to 1. But the whole table won't necessarily sum to 1. So by factor, we're just generalizing this this property of a table over variables. So we're going to use factors a lot and operations on factors for all of our probabilistic inference. So the reason it's useful to define this as a term is often we're going to write something like f of a b, or actually let's use the terminology we're going to use in the next section, in the variable elimination section, which is tau of a b, tau being a specific factor. We're going to write this as, for example, probability of A times probability of B given A. And what we mean here is we're actually, in this expression, we're trying to write down the whole factor tau of A comma B. So if these were binary variables, this would be 4 numbers associated with this factor. And we're writing it as a function of these 2 other factors. So this is more succinct than saying, well, if we, this is a way to compute for any particular value of A and B, we can figure out the values that go into these respective distributions. When we're doing this computationally, and again, we're doing this algorithmically, so we want to see how this would actually be implemented in a computer. In general, when we write down a factor, we're imagining this as an actual table that we would store on a computer. And we would be doing these computations over entire factors. So if there's a line in our algorithm that says something like compute tau of AB by multiplying together these 2 factors, that is to say that we're going to take in 2 probability tables, both of which exist in memory, and output this other probability table. So hopefully that's clear that we're not doing anything mathematically different. This is really just a notational shorthand and for use when we were to actually implement this in computer code.